Welcome. I'm going to talk about the graphical solution of linear problems. As an example, we have a company which manufactures two products called P1 and P2. Now, there are three limiting factors that have to be considered. And the first one is there's only one shared machine for the production of those products available with limited resources. Then the products are made from a raw material, and there's only a certain amount of that raw material. We're going to assume that only this amount of raw material can be used and that we can't just get new raw material here. So whenever the 720 units are used up, we can't go on producing. Finally, there are some limited assembly capacities only for product 2. Now in this table, we have all the available resources and the requirements for producing one unit. So what this table means is, if we look at the machine for production, well, if we want to produce product 1, then we have to use 1 hour on the machine for producing 1 unit of P1. If we produce 1 unit of P2, then this requires 1 hour on the machine. Altogether, we only have 100 hours available. So that limits the amount of product 1 and 2 that we can produce. Second, there's the raw material where we have 720 units. Now, for producing 1 unit of product 1, we're using 6 units, and if we're producing 1 unit of product 2, then we're using 9 units. And finally, the assembly capacities, they're restricted to product 2, and there is, for the production of 1 unit of product 2, we need 1 unit of this assembly, and we have an available capacity of 60. We're always considering a certain time frame, like 1 month, for example, or 1 week. Now, the question is, how many units of P1 and P2 should the company produce in order to maximize its profits? We know that the profit from 1 unit of P1 is 10 monetary units, might be 10,000 euros, for example. And the profit from 1 unit P2 is 20, so that might be 20,000 units. From that, we already see it's more profitable to produce product 2. However, product 2 needs more resources here and there. So the question is, how much P2 can we produce and how much of P1 can we produce? What we're going to use is, we're going to use variables x1 and x2, and x1 stands for the amount of product 1 that we're producing, and x2 stands for the amount of P2 that we're producing. Now in the next step, we're going to write down this problem in its mathematical formulation. So we're going to write down the problem in terms of x1 and x2. Now, the function that tells us how much profit we're making is 10 times x1 plus 20 times x2. If somebody would say it would be good if we produced, for example, 30 units of x1 and 15 units of x2, then we can calculate the amount of profit that we're making from this decision. So our goal is to maximize this. So I'm going to write this in this form. I'm going to write maximize this. And the function that we're looking at is called f of x1 and x2. So this is a function of two variables, x1 and x2. If we didn't have any restrictions, the solution would be clear. The best solution would be to just produce as much as possible. That would maximize the profit. Actually, the profit could be infinitely large. We have those restrictions, and now the question is, how can we write down those restrictions? Now, what we're going to see is, once we have this table here, it's pretty easy to write down those requirements. What we can do here is this column P1 relates to x1 and this column relates to x2. So we can just take the information here line by line and transfer it into a mathematical model. So we can write x1 plus x2. What this means is the amount of x1 that we're producing plus the amount of x2 that we're producing. And now this must be less or equal 100. That's the first restriction from the machines. The second restriction is 6 times x1 plus 9 times x2 should be less or equal than 720. What this means is, again, if somebody said, let's produce, let's say, 100 units of x1 and 50 units of x2, that would mean we have resources of 600 and here we have 450, and that would be greater than 720. So producing 100 units of x1 and 50 units of x2 is not a feasible solution. The last restriction is x2 must be less or equal than 60, because we only have those 60 units for assembly. These three requirements are almost complete. There is one requirement that's always necessary, and that's the non-negativity requirement. So except for some rare cases, x1 and x2 must always be greater or equal than 0, because it doesn't make sense to produce negative units. So if there is a solution which says x1 should be 5,000 and x2 should be minus 4,900, then this clearly doesn't make sense because we can't produce any negative units. If this were a system of linear equations, so if we had equal signs here, then it would be quite clear what to do. We could just solve the system of linear equations. However, it's not a system of linear equations, so we have to find the solution somehow differently. So what we're going to do now is we're going to translate those equations here into something more meaningful, into something which has a graphical representation. So what we're going to do is we're going to write it this way. I'm going to write x and y instead of x1 and x2. So I'm going to write x plus y is less or equal than 100. 6x plus 9y is less or equal than 720. And y is less or equal than 60. And x and y must be greater or equal than 0. Now if we take those equations, this might look a bit more familiar. And what we can do here is we can rewrite them. So if we take the first equation, equation number 1, can be written as y should be less or equal 100 minus x. The second equation, the second inequality, of course. So the second inequality should be written as, first of all, 9y is less or equal than 720 minus 6x. And if we divide that by 9, we have 9 is less or equal than 80 minus 2 third x. And then the third inequality, well, that's just fine in the form it is. Now, what do those inequalities stand for? Now, the first inequality, y is less or equal 100 minus x. If we draw this graphically, x and y, and now we can draw a line here. This is 100, this is 100. And now, since this is an inequality, everything that's below this line fits this inequality. So y less or equal 100 minus x means everything here in the blue region, including the line. The second one is y is less or equal 80 minus 2/3 x. Now again, we can draw this as a small example. This line starts here at 80 and here meets at 120. And again, this inequality means everything below this line is in that region. So for all the points in this blue region, it's true that y is less or equal than 80 minus 2/3 of x. The final restriction is that y should be less or equal than 60. So this is very simple to draw. So if we just have this point here at 60, then if we draw a horizontal line, everything below that line fits into this description here. We also have that x and y must be greater or equal than 0. So this means the region we're actually talking about is limited to this portion here, to this portion, and to this one. Please note that this region here is infinitely large. It extends infinitely long to the right-hand side. All those three restrictions must be met. So we have to put them together into one picture. So this is x and y. And now we're putting everything into the picture. So we have 100 here, 80 and 60, 100 and 120 here. The first restriction goes from 100 to 100. The second one from 80 to 120. And the last one. So the so-called feasible region, the region where the allowed values are, is the blue one here. So I'm just going to sketch that like this. So this is the feasible region, and that's somewhat the allowed values. If we had a value which is, for example, at this position here, so something like 110 and 50 or so, that wouldn't be an allowed value. It's not an allowed solution because it requires too much resources. It's not in the feasible region. We know all the allowed values. but which value is the best value? Well, obviously, one possible solution would be to just produce nothing. If we produce 0 units of product 1 and 0 units of product 2, that's certainly a feasible solution, that's allowed. However, it's not a very good solution because we're not making any money. So the question is, what is the best solution? Now, the best solution must be somewhere in the region up there or right to the far right. So how can we find the best solution? Now, what we can do here is we can just look at how different solutions behave. If you just make the assumption, let's say if we were producing x1 20 units and x2 10 units. That would mean that f is 10 times 20 plus 20 times 10, and that's 400. So where is this line of, where's this point that this refers to? Or actually, there are several possibilities to get a value of 400. Another possibility would be to say, if we produce x1 0 and x2 20, that would also lead to f equal to 400. So there are different possibilities to get a value of f of 400, to get a profit of 400. So where are those different values is the question now. So what we can say here is, if we have 10 times x1 plus 20 times x2 equal to 400, or actually we used 10x plus 20y equals 400. Now we can rewrite that as 20y is 400 minus 10x, and that's y is 20 minus 1/2 x. So we can draw this line into the picture. If we draw this, it looks something like that. And now this is called the F line. Clearly, this isn't the best solution yet. So what we can do now is we can shift this F line. So we can shift it slightly here, and then another parallel line, another one, another one. Now we're still in the feasible region, but at some point, well, we get very close to the edge, and we will find this is the largest possible line. So this line has just this one point where it connects to the feasible region, and this marks our optimal solution. So this point here up there is the optimal solution. And what we can do now is we can find out what is the solution. So clearly the y value of this point is 60. And now, depending on how nicely we made this picture here, we will find this value here on the x-axis more or less exact. If you made a very nice picture, you'll find that the solution here is 30 and 60. And now this means x1 equals 30 and x2 equals 60 is the optimal solution. Every other point here is also a solution, but it's not an optimal solution. If we plug in 30 and 60 into the profit function, we get 1,500. And that's the largest profit that we can achieve.